today's our last lecture for this course. We'll finish this voltage stability section. On Friday, we have a Zoom meeting to present your project, course project. Then it will be concluded for the entire course. So before the midnight today, you're going to submit the quiz number 5, right? For small signal stability and transient stability. And by tomorrow, you're going to submit another quiz, number 6, for voltage stability. So there will still be a homework on voltage stability, which is due next week. All right. So I'm sorry this week will be a very busy week. The good thing is we really can learn very useful stuff. I believe you will find some knowledge from this course useful, unless you don't want to study anything about power system. Okay. So if you missed the first lecture about voltage stability, so on last Thursday we used this radio system to derive a very useful tool, which is called PV curve. Basically describe how the voltage can change with increased load at the end of this radio system. So you have a constant voltage source supporting a impedance load. By reducing the impedance, you will increase the current, and so the load of this impedance will first go up and then will decrease. So if we draw how the voltage change with the power, so we'll have this PV curve. So PV curve. So if you operate at load which is less than so it basically has critical point. We call it a nose point or knee point. So that is the boundary of the voltage stability. So if you have the load less than this value, this 100% of the maximal load, basically if you draw a vertical line, it will intersect with the curve by 2 points. So the top one will indicate the SEP, the stable equilibrium point. And the lower one will be UEP, unstable equilibrium point. So we'll increase the load, and finally, the distance between the stable and unstable equilibrium point will become shorter. Finally, those 2 points will merge to the same equilibrium point, and that equilibrium point is now stable. So which means the system doesn't have any stable equilibrium point, which means the domain of traction of the stable equilibrium point will be 0. So that's mechanism of voltage instability. We call it a saddle node bifurcation. So this one, saddle node bifurcation basically means saddle means there's unstable equilibrium point, node means stable equilibrium point. When they merge, the bifurcation happens. At the beginning of this lecture, we'll talk about another useful tool. This PV curve is good to study how far you're away from the boundary of stability for your current loading condition. And you can draw such curve for many different power factor, right? So if you determine the power factor for your system and you increase the load for one area or at one bus without changing the power factor, so voltage will decline or change according to that specific the PV curve. For instance, if power factor is 1, so it will change following this PV curve, and this will be the stability limit. So you need to make sure to operate before that point is reached. So PV curve is very useful to estimate how far you're away from the critical point. But the question you may have will be, what if I can add some control? If I can add some control to inject some Q to the load bar to help increase the margin of stability. So PV curve is not very straightforward. So I have to introduce another tool, which is called a VQ curve. So that one will give you more information about control. So let's talk about VQ curve. So this curve can tell you how effective the ready power or control can be added at some location. So for instance, we still talk about this radio system. We study additional ready power injected to this load bus, and we study how this Q can improve that voltage. we need to figure out the function on how the voltage will change with Q. So that one is called a VQ curve. Keep in mind, this Q is not that Q. It's not the load of the Q. It's actually additional Q injected to this bus. It can be done by a like capacitor or SVC, stay-calm, or a simultaneous condenser. So any voltage controller we learn from the voltage regulation control session. So here, just to make the derivation simpler, we don't know what happened there. Let me turn off that one. Okay, so let's assume the line is a lossless line. So the impedance angle will be 90 degrees. So that will make all the formulas simpler. So the compressed power from the source will be voltage can be calculated by this formula. So here, because the QI is as injected, reactive power will compensate part of the reactive load. So finally, total compressed power from the source will be PR as a real power, but for reactive power will be a QR minus QI. Okay, and so we take the real part, which is active power, and reactive part, imaginary part, which is reactive power. So you see, we already have both voltage and magnitude and the Q injection in the formula, but we want to merge those two equations into the same function. One thing we can do is we can eliminate the angle delta. The delta is the angle of the source, which is not very important to determine how much control to be added. So from first equation, we can solve sine delta. Second, we can solve cosine delta. So, and then we can just merge the two equations. So we have this formula. So this one will be the equation telling the VQ curve. To make this equation more useful, we want to specify the active power, which means when we study the control for this system, we don't want the active power PR to change. So we want to make this PR to be fixed. Because PR is fixed, if the power factor also constant, so QR is also fixed. So we only change QI here, and then we study how the VR will change. So only QI and VR are the variables of this equation. So if we know the power factor angle phi, so the QR would also depend on the ID power and power factor. Okay. So then we can draw the VQ curve. If we know PR and phi, the curve will be like this one. X will be the voltage magnitude, Y will be the injection of the reactive power. So I draw a horizontal line at 0, which means indicate this is the condition without control, because QI is equal to 0. So when you don't add any control, there will be one line, and that line intersect with the VQ curve at 2 points. So this green one will be a stable equilibrium point. So this one indicates the voltage will be slightly higher than 0.9 per unit. And there's another intersection point that corresponds to voltage, which is very low, around 0.2 per unit. That's unstable equilibrium point. So the other one will be unstable equilibrium point. So if you can solve the voltage power at those two equilibrium points, which are same as the two equilibrium points you can find from PV curve. So on PV curve, if you draw determining some loading condition, you also can get ICP and UEP, and those two should be same as the 2 points we got from a VQ curve, because both curves describe the exactly same system. So if we increase the IT power, okay, this VQ curve only indicate one condition with a PR phase, but if we increase the power, increase the load, the VQ curve will move up. Okay, so the curve may look like this one. and which means the two equilibrium point will get closer. So when you further increase the load, finally, the two equilibrium point will merge. That is exactly what happened with the saddle node bifurcation. All right, so you see the difference from a PV curve. PV curve represent how the voltage change with the increase of PR. So which means that curve represents many conditions. So you continuously change the IT power, change the PR, how the voltage will decline. But for VQ curve, that tell you how the voltage change with injection. So if injection is 0, which means you have no injection from any additional ready power source, and if you still want to change the loading condition, you need to draw many different VQ curve. But if you want to study control, you don't change the power, you don't change the load. So this single VQ curve will be enough, which means if you here, let's use this VQ curve to get some idea. So right now, this intersection point, which is stable equilibrium, correspond to voltage level, which is slightly higher than 0.9, which is not okay for some high transmission system. So if you want to have 1.0 per unit, so you draw a line up, so intersect with this point. So that point indicates how much QI is needed. So you need to have QI, which is roughly like 0.15. Then you can increase the voltage to about 1 per unit. Okay. Definitely, there's some other cases when you have a QI equal to 0, but the voltage is too high. Then you want to switch in some shunt reactor. You actually need to inject some negative Q to bring the voltage down. So this curve tells you how much reactive power you want to inject or consume from the system to maintain the voltage at desired value. So basically, you draw the VQ curve at any voltage you like, and you draw a horizontal line. The horizontal line intersect with the VQ curve. That value will tell you how much Q you need to either inject or consume. So if it's a positive value, you need to inject additional ready power, such as capacitor. But if you want to lower the voltage, if that Q is negative, which means you need to consume some ready power, switch in some reactor. Well, we can draw many VQ curve together, but here you need to, each VQ curve you need to specify the PR and the phi. PR is the active power load, and phi is the power factor. So here, if we assume power factor to be 1, and by increasing the load, you can draw many VQ curve. So for instance, if we start from this VQ curve and that intersect with the system at this point, and definitely there's another unstable equilibrium point. So now you increase the load. You increase the load from 50% of the maximum limit all the way to 100% limit. So when you reach the 100% limit, so the VQ curve will move up and become tangent to this line with 0 injection. So which means if you don't inject any ready power, you won't be able to operate the system stably at the maximal power. If you want to make sure the system is still stable, you need to inject some ready power. For instance, if the injection is 0, so the critical point will have voltage like between 0.6 and 0.8, and that point is critical point. If you want to operate at 100% limit, but you still want to maintain voltage at 1 per unit, so you need to draw a vertical line intersect with the top curve, and then you draw a horizontal line. So this one indicates how much Q you need, okay, for the minimum to maintain the voltage at 1 per unit. All right, so just to summarize, the VQ curve shows sensitivity and variation of a bus voltage with respect to the reactive power injected at the bus. They indicate the QI required in order to maintain the bus voltage at desired value VR. a VQ curve is generated by applying a fictitious var source, because here you study what voltage controller, what var source can potentially increase the voltage to desired value, right? Before you knowing what you want to put onto the system, there are many different voltage controller. It can be generator, it can be a switchable capacitor bank, can be SVC, Stacom, single condenser. But before you decide what is ideal for you, you can just assume there's a fictitious var source. So usually we can use the most powerful voltage controller, which is like generator. But definitely, if you place a generator at any load bar, that's not very practical. So you can use some synchronous condenser. Synchronous condenser basically just like a motor, a synchronous motor with all the excitation control system. Okay, so you apply this synchronous condenser with increased the var value to the system, and you can draw the VQ curve for this loading condition. All right, so by observing the VQ curve, we know the critical point, which is this line, separate each VQ curve into two sections. The section on the right will have all the slope positive, right? All the slope positive. On the left-hand side, we'll have all the slope negative. So which means if you see the positive slope of the VQ curve for your current condition, which means your system is stable, okay? If your system is unstable, if the slope is negative, you need to inject certain QI, such as that slope become positive. Okay, so this can be very useful criteria to judge stability. So when you draw the VQ curve for the condition you operate the system around the injection, the QI, if this derivative become positive, the system it will be stable. If it becomes zero, which indicate the bottom point, we have a zero slope, the system will be at the stability limit. If it's negative, system will be unstable. Okay. If we connect the side of a VQ curve to maybe some pivot curve, because the VQ curve of in the top figure were generated from the same radial system, right? The same system as the pivot curve generated. So how can we connect those VQ curve to the bottom, any one of from the bottom for the pivot curve? Please notice that the group of VQ curve on the top correspond to a power factor of 1. Power factor 1, which means it only corresponds to one of those pivot curve, which has a power factor 1. So the whole set of a VQ curve correspond to just single pivot curve on the bottom, which is this one. So each VQ curve indicate one condition, or maybe one operating point on this pivot curve. Okay, for instance, if we start from the operating point, which is at the critical point, so this corresponds to the VQ curve, which has load at 100% of maximum value, which correspond exactly to this condition at critical condition when the P increase to the maximum value, right? So those 2 points correspond to exactly the same condition. It's just is that equilibrium projected to different spaces. So when we move this point to the right, which correspond to the load decrease from 1.0 to 0.5. Okay. So what does that one mean on the pivot curve? So that point will move to the left on the top portion of the pivot curve. So that's what happened exactly. Okay. Similarly, if you study maybe another pivot curve with this is like a 0.95 lagging power factor starting from critical condition, move to the left. that corresponds to this point. Okay. So why it start from here? Because the second condition corresponds to a lagging power factor with additional reactive load at that bus. So that additional reactive load, if you do the calculation, that's about 0.25 per unit. Okay, so which means that draw a line, so it will indicate the operating condition moving along this negative 0.25 per unit reactive power condition. So this just give you an example on the PV curve and the VQ curve for the same system. They do have very strong linkage. It's just a projection to different spaces, depending on which space is useful for your study. If you want to understand how far away from the boundary, so PV curve will be very useful. If you study how much control will be needed, the VQ curve will be good. All right, so in the previous slides, we introduced the VQ curve, but we didn't assume what var source we can utilize. Okay, similar to there's one example I talked about on last Thursday. So we derive the PV curve, but we don't know what load we're going to operate the system. So if the load is constant power, it will become tangent to the PV curve exactly at the critical point. But the load is a ZIP load which is a quadratic function, so it will intersect with the PV curve at a different point. So which means if you don't have better information about load model, you can always assume a constant power load, but that will give you most conservative result. Okay, but if your load has some constant impedance component, the system doesn't have voltage collapse at that critical point. It will happen later. How late depend on the load model. So similarly here, if we use VQ curve to study control, it tells you how much reactive power you want to inject to the system. But there's no such like a constant reactive source you can guarantee to give you that much of reactive power, no matter what voltage you operate the system. So you still need to assume some practical var sources to do the study, right? So here, let's just consider maybe reactive compensator, which is made by the capacitor banks, for instance. So how can we utilize VQ curve to study what reactive power to be injected? So for this reactive compensator, it's basically we can assume it's made by the bank of a capacitor or reactor. And this capacitor, this compensator has some automatic control. It can increase the reactive power compensation in order to increase voltage. If this is like more like a passive capacitor bank made only by reactor or capacitors, so this Q will be calculated by this formula. So it's not like a constant QI independent of voltage magnitude. It will be a quadratic function of a voltage. So because this IC can be something we can adjust, but once you fix the IC, the Q will change in the quadratic function of voltage. So it's not ideal reactive source. So those curves are still VQ curves, but we also draw some other broken line. Each one will just indicate just a characteristic of this compensator as quadratic function of voltage. So each of them will be a quadratic function of voltage. So for instance, for this one, so the top curve, that says 950 MV megavar. What that means, if you can operate the voltage at exactly 1.0, then you draw a vertical line. So it will intersect with that characteristic at the point B. Okay, so that point B will indicate 950. But if you cannot operate the system at exactly 1.0 per unit voltage, so that var will change as quadratic function near that point. So this is different from ideal var source. Ideal var source will have a horizontal line, right? It give you exactly that amount of reactive power, no matter what voltage you operate the system. But this is not ideal. So it will ask quadratic function. Similarly, for each value, that also tell by a quadratic function. So their differences are mainly in the value of XC, with the reactance of the inside of a capacitor or inside of a compensator. Okay, so we can draw one direction. So because you see the value, the value increasing in this direction. Definitely the reactive power injection to the system will be growing, but that is caused by the change of the reactance, the decrease of the inner reactance. So when the XC decrease, okay, so the QI will increase. So this is true only for the voltage near the 1.0 per unit based on their design. All right. So then there will be a question. So if you let's see, if there's no compensation, without compensation, and for this current system must be unstable. Why? Because you see here, so all the VQ curve actually above 0. So here is the 0. 0 means there's no injection. So when the system has no injection, the VQ curve doesn't intersect with the x-axis, right? So there's no intersection point. The system cannot be stable. So you have to inject certain Q. If it's ideal QI, so you just draw a horizontal line, but now it's not ideal. It's actually a quadratic line. So which means we have to inject some reactive power through this compensator. Let's study one condition. One is the point A. At point A, okay. So at point A, the VQ curve slope is higher than the slope of that quadratic function for the compensator characteristic, because this direction will be the increase of compensation. So if you want to increase the voltage, you can increase the compensation. This is the direction you want to increase compensation by decreasing the IC. So you are going to change in this direction. So the voltage will be improved because this is in this direction, both voltage and Q will be increased. Okay, so when you reach maybe to the new voltage location condition, you can stop. So this control can be stable. Okay, but if you study another condition at B, so if this B has voltage not good enough and you want to improve the voltage, you still go to the same direction. But in this direction, what happened? The voltage will decrease because B prime is in that direction, but B prime has a lower voltage than B. So which means when you compare the two slopes, one is from the VQ curve, the other from the compensator characteristic. So when the VQ curve has higher slope, so such control can be successful. Otherwise, that will fail. So the key will be comparing the difference in the slopes of the VQ curve and the compensator. Okay. So for the B condition, this control will fail. So when you study the system with a var source which is not perfect, which is like quadratic function of a voltage, you do need to draw the both characteristic and their intersection point, then compare the slopes of the two curves. You need to make sure the VQ curve will have a higher slope. So at point B, the voltage will be unstable because the slope of the VQ curve is actually smaller than the slope for the capacitor. So system will be unstable. And such control cannot stop because the controller believe that is still the right direction to go, but finally it didn't increase the voltage. The voltage further decreased. So eventually it will reach to the critical point to collapse. Another example is, what if we have a generator behaving at the var source of the radio system to provide reactive power. Generator can also be it may not be the ideal var source either, because each generator will have some var limit. So let's assume this condition, and we add a small generator at the middle point of the radio system, and we use this small generator to provide some var. We can also use PV curve, VQ curve to study the control. The action of the generator AVR, which is automatic voltage regulator, will provide some reactive power to support the voltage. Under normal condition, the generator terminal voltages are maintained constant. Okay, because AVR can maintain, if the AVR is trying to maintain this voltage, so this voltage will be treated as constant voltage. So when you draw the PV curve, you can use this voltage as a source. So the generator AVR control will make this bus to be a like constant voltage source. But since the generator has the var limit, it only operates within this D region, right? We studied the D chart. So each this region, the boundary is determined by a number of current limit, including the field current. There's also like a stator current, right? So there are many limits together determine this region. So S indicate the P and Y indicate the Q. So when it reaches the boundary, so that will reach the limit of the generator. So during some condition, the voltage are either low or high. So the var output of the generator may reach to limit. It can reach to the top limit or maybe the bottom limit, depending on this generator need to provide or consume reactive power. Then in such cases, the voltage VI will not be constant anymore. So you cannot treat this VI as the constant voltage source. So now the constant voltage source will become either this ES, which is remote bus, which can be considered infinity bus, maybe inside of the generator. So let's see if the constant, if the field current reaches the limit, and the field current will become a constant. So right now the constant voltage will be EQ. EQ is actually because EQ is basically proportional to the field current, right? Remembering the EQ is basically proportional to IFD. So when the exciter reaches the limit, and FD will become constant, it will operate at the limit. Then the EQ will be really the internal constant voltage source. And then you still can utilize the radio system we talked about in the previous slide to derive the PV curve. But right now you need to use this EQ. And if there's any impedance, you also need to add impedance, which is the cylinder readings inside of the generator. So you need to add this cylinder readings to the impedance. So the total impedance will be increased. So that will change the PV curve. Okay, so here the figure draws two PV curve. The first one, the black one, indicate if the VI, which is the where the generator is connected. Okay. So if VI is regulated, so VI will be constant. So you're going to use VI and readings between the VI and VR to draw the first PV curve. Okay. And assume right now you operate at maybe this point. it still has a lot of distance to the critical point. The critical point will be the point B. The system is still stable in terms of voltage. But if you reach the current limit, that will make EQ become constant. Okay, so this bus will fail. That one cannot maintain the constant voltage. And so you need to treat EQ as the constant voltage, and the reactance, you need to add the signal reactance. You need to use EQ and the line reactance together with signal reactance to redraw the PV curve. So the new PV curve will be this one. So if that switch happens, so your optimum point will be suddenly become unstable because the original PV curve has certain distance to the critical point. But if the system switch to the new PV curve, it's already beyond the limit. So system can become unstable. So operator need to be aware on when such switching can happen. Okay, really depend on how the field current limiter is designed for the generator. Okay, so from this example, we cannot use the bus voltage magnitude based on how high the voltage magnitude is to determine the voltage stability, because we don't know when the transfer limit will happen. Because if the generator is still within the rated power limit, it can have enough distance, but when such switching happens, it can become very close to the critical point. Another switch that can happen will be this type of condition is called the limit-induced bifurcation. It's also a type of bifurcation because before the switch happens, the system may have still have two equilibrium. Okay, so if this is original condition, it has a stable equilibrium point and unstable equilibrium point. So there's enough distance between the stable and unstable one. But when it switch to the new PV curve, it suddenly the stable equilibrium point disappear. So that's similar to the saddle node bifurcation. But for saddle node bifurcation, such changes continuously, right? But for this case, that can suddenly jump to a condition without this transition. There's another question we can ask. What if this generator is tripped? Okay, so now we consider one switch, which is when the field current reaches the limit, and the PV curve 1 will switch to PV curve 2, right? And what if the second switch happened, which is the generator is tripped? Because if the generator is operated at over limit condition too long, the generator can be tripped by protection. So if that tripped, so can we use those two PV curves anymore? Either one? So none of them will be, neither one will be correct. We have to redraw the PV curve based on this voltage and the total reactance. We have to redraw another PV curve. So using that PV curve, we'll know where the condition will go. So one possibility will be if you use that ES, which is like remote voltage and the reactance for the entire transmission path, this can be the new PV curve. And the original condition is because it already has a power higher than the limit, so the system will collapse. Okay, so for this case, after the first switch happened, the condition A will get closer to the critical point in the new condition on the second curve. And when the generator trip, it go to the curve number 3, the system will collapse because that loading condition cannot intersect with the third PV curve. And this is called limit-induced bifurcation. Any question? Okay, so from these slides, we're going to generalize the measures based on PV curve and the vehicle curve to a bigger system. We talk about the modal analysis. So modal analysis has been introduced in the small signal stability section when we studied the oscillation damping for the dynamic of generator. But here we can use similar measure, but this is the modal analysis will be conducted on the power flow model, not the dynamic model. The modal analysis will linearize the power flow model for a specific operating condition, which could be a power flow solution. So we'll study the sensitivity on how the voltage can change with the power. And so all the analysis will be performed based on the Jacobian matrix. Definitely the Jacobian matrix here is for the power flow model. So we have power flow equations at each bus. The first equation calculate P, second equation calculate Q. Okay, so both equations are nonlinear. So everybody has been familiar with those power flow equations. And if you decide operating condition, and you can linearize the power flow equation by using this linearized version. So this linearized version is useful to solve power flow in the Newton-Raphson approach. So in Newton-Raphson approach, basically you just use those Jacobian matrices to iterate as based on initial gas until you can convert to any power flow solution. But here we can use the same Jacobian. So Jacobian matrix has 4 components, 4 blocks. So for instance, block P theta means how the P change with theta, right? And block J QV determine how the Q change with V. So definitely we know that this is actually the most important part for the modal analysis on voltage stability. So if we study the voltage stability for specific loading condition, we can assume the delta P is 0. It doesn't change for the active power. So now the reactive power delta Q will be equal to there's a 1 Jacobian multiplied by the change on the voltage as a vector. So JR here is actually can be easily proved. That one can be calculated from here. So basically you just you let this one be 0, and from the first equation you solve a theta, then you plug into a second equation, then you have finally you have this solution. Then you know the voltage change will depend on this inverse of the Jacobian multiplied by the change on the reactive power injection. All right, so this JR tell how the voltage can change with Q, or how the Q can change, how the injection need to be determined based on desired improve of the voltage, which means this is actually a generalized version of a VQ curve. Okay, because if delta V, delta Q, they both have just one dimension. This is exactly VQ curve. That JR will be the slope at the operating point, right, near the operating point for the VQ curve. So this is just a like generalized version for a set of VQ curve. So delta V, delta Q will include many buses of the system. So JR here is a reduced Jacobian matrix of system and represent the linearized relationship between the incremental change in the bus voltage magnitude and bus reactive power injections. To identify voltage stability, we can utilize that matrix of JR. And we can solve eigenvalues and eigenvector, similar to the small signal stability analysis for dynamics of the generator. let's assume the JR as a matrix can be diagonalized, which means it will multiply by a non-singular matrix Kasai on the left-hand side, and also multiply by another non-singular matrix eta on the right-hand side. And the lambda here will be a diagonal matrix. So if we can decompose this JR into the product of three matrices, and the middle one will be the diagonal matrix, which means it can be diagonalized. So that diagonal matrix will have all the entries on the diagonal element being the eigenvalues. And that Kasai on the left-hand side or eta on the right-hand side, I basically tell the eigenvectors. And the Kasai will be the left eigenvector, and eta will be right eigenvector. Oh, Kasai will be the right eigenvector, and the eta will be left eigenvector, because Kasai is going to by definition, it will be Kasai right eigenvector, so it will be a multiply from the right. Okay. I think, yeah, so it will be JR right? Yes, and which means this. So this Kasai, if we each column is a vector, it's a column vector, and we make a matrix and multiplying the JR matrix from the right hand side, that is equal to the same matrix multiplied by that diagonal matrix from the right hand side, which means if we call the Kasai to be the inverse of eta. Then we'll have eta on this side. That's how we can decompose this JR into the product of the three matrices. Okay, so we can compare the eigenvectors, eigenvalues, or the regional matrix here to the similar concept from the small signal stability analysis. So for small signal stability analysis for generator, we studied the eigenvector for the matrix A. Matrix A is actually the linearized model of the differential equation. And we define right eigenvector, we call it phi, right? So each column of this phi matrix will be the right eigenvector. And each row of this psi matrix will be the left eigenvector. And diagonalized the A matrix will be this lambda made by all the eigenvalue. Okay, so you see here, so phi will correspond to Kasai, right? And the psi correspond to eta. And this lambda is same as lambda. So basically, here we utilize the same method to different model. For small signal stability study, we utilize the method modal analysis for the linearized dynamic model. But in voltage stability, we apply this same method to the power flow model. Okay, so next from here, because we can replace this inverse of a Jacobian matrix by the diagonalized version. So we'll have this equation. And if we spell out what happened in here, which is like a summation of many atoms. So each atom has a product of one right eigenvector and one left eigenvector divided by the eigenvalue. So I here, that's the index of the eigenvalue. So if the system has a dimension of n, so it will be n lambda I. So each lambda indicate one mode. So here we assume the eta will be inverse of cosine. All right. So next we can we keep the inverse of lambda, and from this one we can define a lowercase v and the lowercase q. So from that equation, we know the lowercase v will be the eta transforming the delta v. So we call this one as the vector of a modal voltage variation. And the lowercase q is actually eta transforming delta q, which is a vector of a modal reactive power variation. So if we compare this equation, so if we only just pick one element, so this is completely decomposed version of the linearized power flow equation. Because although we still write in the vector form, but because lambda here is a diagonal matrix, so it has decomposed eigenvalues. So if we pick each eigenvalue, so it will correspond only just to a single v and a single q. So with the same index I. So the original power flow equation, if we start from here, that's original power flow equation, linearized power flow equation. So when we get to this point, it becomes an individual linearized version of power flow equation. And each equation tells how the voltage change with Q. So that is exactly one VQ curve. Okay. So if you pick any single equation here with any I, so that tells you the VQ curve for each individual mode of voltage stability. So that has similar idea to this equation. Remembering for small signal stability study, we utilize the diagonalization and we decompose the system into regarding the eigenvalue. Finally, in the new space of Z, each Z state variable is independent from any other variable, any Z. So this one only is categorized by a single eigenvalue lambda. So here we generate the we generate decomposed version of the power flow, and this one categorizes one single mode of voltage stability. So if every lambda here is a positive, the entire system is stable in terms of voltage everywhere. But if any lambda is become 0 or negative, the system will become unstable. Okay. Let's start from here. This is what we defined from a previous slide. And if we study a 3-bus system, so for the 3-bus system, definitely you first, I ignore the first few steps. You write down the power flow equation for this 3-bus system, and then you linearize the system to get to here. All right. Starting from there, and you solve the right eigenvector. You solve first 3 eigenvalue. So for each eigenvalue, you solve the eigenvector. And you make the 3 right eigenvector be a matrix 3 by 3. So that will be the matrix eta. And using that eta and its inverse, you can diagonalize the regional Jacobian into this the matrix of eigenvalue. So this one will be the same as that general equation. So we know there's a 3 eigenvalue, which means the system has 3 modes of voltage stability. So for instance, if we pick a mode number 1, which corresponds to lambda 1, so you will pick the first equation. So this lambda 1 will be equal to the first row multiplied by this column and this row multiplied by that column. So we'll generate this equation. And we can define everything here as Q, right? Q1. And everything there as V1. So we'll have this equation. This one will tell when you inject Q1 and how the voltage will change regarding this number 1 mode. But definitely that Q1 is not actual Q1. The Q1 is actually the linear combination of relative injection at many different locations, 3 different locations. Also, that voltage is not a single voltage. It's actually linear combination of all the bus voltages. All right. So for this mode, that corresponds to a radial system. So VQ curve is developed based on a single radial system. But when we generalize this idea by mode analysis, each mode will have corresponding VQ curve. And that one can be categorized by this equation, by equation such as this one. Okay. All right, so we can summarize the conclusion from a mode analysis. So if you linearize the power flow equation and you get a JR, then from JR you get all the eigenvalues. So each eigenvalue, lambda I here, defines a voltage stability mode. That actually basically just categorized by some fictitious radial system equivalent. So this lambda determine how close the condition is from the voltage stability. Basically tell you the stability margin. So if this lambda is positive, which means you have positive stability margin. Okay. If it's negative, which means you already passed the limit, the system becomes unstable. If 0 means it's right on the limit. For positive lambda I, so the ith modal voltage and the ith modal reactive power variation are in the same direction, which means if your voltage control is designed as by increasing reactive power, you want to improve voltage, such control can succeed because lambda is still positive. But when the lambda becomes 0, you still try to increase the voltage by increasing the reactive power. That may not succeed. And if it becomes negative, that will fail. That will make the voltage even worse. The negative lambda, which means the margin has become negative. Okay, so to quickly summarize the modal analysis voltage stability study. First step is you list the power flow equation, determine a specific operating condition, a power flow solution. Then you linearize the power flow equation to find this JR. JR here assume the ideal power doesn't change, right? You eliminate the delta. You get the relationship on how the delta V depend on the delta Q, how the voltage change with the reactive power injection at any bus. Then for this Jacobian matrix, you solve eigenvalue. Okay, if all eigenvalue are positive, which means system is stable. You're far from any voltage stability limit. But if it's any lambda becomes 0 or negative, which means for that specific mode, the voltage will become unstable. So that mode corresponds to some radial system equivalent, which can be categorized by the system, the radial system on that top corner. And for that case, you need to inject reactive power to improve the voltage. So you can use the VQ curve for that mode to determine how much Q you want to inject to improve the voltage. Okay, so you remember in the small signal stability, we mentioned one concept, which is a power participation factor. Participation factor is very useful because it utilizes both the mode shape and mode composition to determine the two-way linkages between the mode and the state. Okay, so for any participation factor to be high, that will be the ideal location you can implement the control. So here we can borrow the similar concept. So we start from this equation. And we notice actually this item is actually tell you how the voltage can change with Q. If we focus on single bus, we just focus on bus K. This is like bus K. So we'll pick one element, one partial differential. That one can be calculated based on this expression. So we pick the case element from the right eigenvector, and we also pick the case element from the left eigenvector. So we calculate the product of the psi ki and eta ik divided by the eigenvalue. So that one will tell you the how the voltage will change with Q at bus K. All right, so we recall the definition of the partition factor. PKI is defined to be the product of phi ki and psi ik, because there K means the state variable K, right? I here means the mode I. So PKI will means the partition factor of the K state variable in the ith mode. So here we can define similar concept, which is partition factor based on the product of a psi ki and eta ik. So K here is the bus number K. Then this partition factor will tell how much this bus K participate in mode I. Okay, because mode I can be any mode which can have potential voltage instability. So when you calculate all the eigenvalue, if there's any eigenvalue which is negative, that mode will indicate a voltage instability mode. Then for that mode, we need to identify which bus participate in that mode based on partition factor. So now this one will be very useful. And if any bus has high partition factor into that unstable mode, that bus will be the ideal location to do the control. So just similar to the small signal stability analysis, we can define bus participation factor as this one, just simulate just this product. So now we know the voltage at bus K change with local reactive power injection is equal to the summation of many atoms. Okay, each atom is just the participation factor into each mode at that bus divided by that eigenvalue. So this PKI will determine the participation of bus K in mode I. In other words, the contribution of this mode to the VQ sensitivity at bus K. The absolute value will tell how efficiently a remedial action at bus K can stabilize this voltage stability mode, can improve the voltage. So all bus participation factors of the system together determine maybe some critical buses or area associated with each mode. For instance, in the case one, when you solve all the eigenvalues and calculate the participation factors for all buses, in case one, you'll find very few buses have very large participation factor. So which means your voltage stability problem will happen from a local area. So you only focus on voltage stability static control in that local area where the participation factors are high. Another case will be many buses have very similar participation factor, which means unfortunately your voltage stability problem is like a regional problem. It's like a more wider area voltage stability problem. So it's harder to be addressed. So in practice, usually you don't have to consider all the eigenvalue, only just pick maybe the smallest 5 or 10 eigenvalues. Then for each mode, you just study the participation factor to determine where to add control. From a Quinter's book, they also give you some other participation factor, depending on what type of control you want to add. If you want to add control to a bus, the bus participation factor definitely will be very useful. Right? But if you want to add control through some transmission paths or some transmission line, or you want to identify which transmission line will be critical, you also need to define branch participation factor. If you want to use generator to do the control, you also need to determine the generator participation factor. So branch participation factors for mode I tell which branches consume more reactive power in response to a reactive load increase. So if the participation factors are high, which indicate those branches are weak, you need to do continuous study at those bound branches, because they can be a troublemakers if there's any voltage issue. So Quinter's book gave you just one definition here. I won't go into the detailed proof. The generator partition factor just tell which generator will contribute more to improve the voltage. So it can be defined by this formula. In the next few slides, I gave you one example how to utilize PV curve, VQ curve, partition factors to study a more practical system, like a 39 bus system. So this 39 bus system has a load area, which is circled here. And inside the area, definitely there's some generator. They also has some generator outside of the load area. And we noted actually there's a bus 530 here that's far away from any generator. So that is actually a very vulnerable location to have voltage stability issues. So we're going to study, first we draw the PV curve at that bus. So what you're going to do to draw the PV curve is you start from initial condition, maybe at the load. So here we assume the load for the entire area will increase uniformly. So we start from a total load at about 80 to 90 megawatt, which is condition number A. Condition A. Then we increase the load uniformly, and we solve power flow until load is higher than 160 megawatt. And we calculate the voltage at that bus. So we utilize the voltage at that bus versus the total load of system. We can generate a second point. Then we further increase the load until point C, and the power flow cannot be solved. So that will be around the critical condition. Then we can draw this PV curve. So we only have the top branch above the critical point, because we cannot solve power flow when the load reaches the higher condition. So we only have this part from A to C. We color them differently. Okay, and next step, we want to study the VQ curve at each of the three conditions. So A will be the initial condition, the light load condition, B will be heavy load condition, C will be the critical condition. We also compare the VQ curve at this bus to the VQ curve at some other buses. We just actually pick three other buses. One still in the same load area, another two is outside of load area. Okay, so we draw the VQ curve for the 4 buses. We have the VQ curve for the 3 conditions. So you see for the condition A, when the load is light, and so when the injection at each bus is 0, so we don't have any control. And this horizontal line will intersect with VQ curve, right, at this point. And the slope all positive, all slope positive at that point. So which means the system is stable. So that is also confirmed from this PV curve. Then we move to condition B. Okay, you see all the VQ curves still have positive slope, but for the VQ curve with bus 530, that one has, the slope has been almost 0. Then when you further change to the condition C, the VQ curve 530 will tangent to this horizontal line. So that indicates the critical condition. If you calculate eigenvalues, and we can pick the top, the smallest 5 eigenvalues. Definitely for each condition, you have a group of eigenvalue. At the critical condition, you see the smallest eigenvalue, lambda 1, is very close to 1, very close to 0. That indicates a critical condition. To determine where to add control to prevent the voltage collapse at condition C, we can calculate bus participation factors, branch participation factor, and generator participation factor. So bus participation factor the top one is 530, right? That's very reasonable, because if you only want to pick one bus to add injection of ready power, you need to pick the bus 530. That's the most critical one. So for the branch partition factor, the top one will be 500 to 520, 500 to 520, which is this one. Okay, so which means any contingency on that branch will more likely cause voltage collapse. For the generator partition factor, top one here is 1311. 1311 is a generator at that location. It's outside the region, but it has highest participation. So if you cannot do any control in the area, so this will be the generator where you can utilize to get more ready power. So based on the analysis, there are a number of control you can try. The first control is definitely based on the bus partition factor, you just inject ready power at bus 530, right? That's very straightforward. Based on the VQ curve, if you inject, for instance, 100 megavar, it will intersect with that curve at a much better voltage. The second condition can be you can do load shedding. So if you have no var source to utilize at bus 530, you can reduce the load. By reducing the load, the VQ curve will move down, and then it will become intersecting with the horizontal line at a much higher voltage. And definitely the third one, if you want to utilize generator, and you can pick the one with highest partition factor. Okay, much time I have. I have 5 minutes left, but I will. So I just quickly talk about this continuation power flow, because if you utilize any software to study, to draw the PV curve, from this example, we don't know the lower part, right? We cannot draw that one. If you only try to increase the load to solve power flow, you will stop at the critical condition. You won't be able to figure out the other part of the PV curve. The continuation power flow is a method you can solve the full PV curve. Okay, so you can even solve the power flow beyond the unstable equilibrium point, or add any unstable equilibrium point. Most of the power flow software integrate continuation power flow, so it's useful when you operate at condition near the critical condition, and the Newton-Raphson approach for the conventional power flow cannot convert, and you can call the continuation power flow method. Okay, so usually you want to utilize Newton-Raphson or fast decouple method to solve power flow up to a location near the critical condition. And then you can switch to the continuation power flow. This one will be very slow, much slower than conventional power flow, but it can help you to track on the PV curve. So basic idea is so if you start from this condition, they will do a predictor. They will do a linear approximation to find the condition B. And at the condition B, it will assume a constant power load. The constant power load will intersect with the PV curve at point C. So we'll keep doing such step until you reach to a point which is higher than the limit. Then you have to assume a different load model with constant voltage but arbitrary load. Okay, that is more aggressive than constant impedance load. So that can guarantee this load characteristic will be able to intersect with PV curve. So beyond that point, you can every time you just basically just draw the load characteristic with horizontal line with constant voltage. So that can guarantee to intersect with PV curve. Okay, so I put some detailed algorithm into this box. I don't go through this box, but just give you an idea. I want to mention one thing. So this measure can give you a complete PV curve, but actually it doesn't guarantee the PV curve under the critical point to be correct. Okay. So you only guarantee any PV curve above this point to be correct, right? Because you do have operating condition there. But when you operate beyond this critical point, even the software can give you that lower part. That may not be correct because you have to assume the load model to be this horizontal line, which has the voltage constant no matter what power. So that doesn't exist in real world. And then let me, if you didn't get, okay. So this is a critical point. If you operate above critical point, you can assume constant power load, okay? Or maybe constant impedance load, whatever. You can make any load, but most of load, you will get similar PV curve above critical point. But beyond this critical point, the load model really matter. It becomes very critical because some load model cannot convert, cannot guarantee you operate at the equilibrium lower than this critical point. So, but some engineers still want to see what the bottom part look like, right? Then you assume this load model, but this load model doesn't exist in real world. It only gives you a complete PV curve. So the purpose to draw the complete PV curve is not to utilize any part on the bottom to do the operation because it doesn't make any sense. The purpose to draw the complete PV curve really to help you to get accurate estimation about where this critical point is. Because if you don't have continuation power flow, let's say if you use constant power load model, okay? So here you can solve power flow, here you can solve, here you can solve, and here many power flow solver will fail. Even you still have some distance. Some better software may help you to get very close to the critical point, but most of software will fail. Then you want to switch to continuation power flow. Then it will continue until identify that point. That gives you very accurate limit of voltage stability. But even it also, if you want, you definitely can continue to give you the lower part, but that part doesn't give you any information. Okay. Because you won't be able to operate at those points. Let me see. I don't have more time to go through the remaining slides, but this slide just lists some causes of voltage instability. You can just read through those sentences. Already upload the slide to Canvas. Let me take a look at what I can emphasize. Yeah. So for the contributing factor, the type changing transformer will be critical. There's some prevention of voltage collapse. So first one, you can use the VAR compensators to inject ready power at some location which have higher bus different factors. Just keep in mind those VAR sources are not ideal. You have to compare their characteristic versus the slope of the PV curve. The PV curve need to have a higher slope in order to make a voltage control successful. Type changing transformer will be a very critical cause of a voltage collapse. So usually, because transformer is not a VAR source, it only just borrow ready power from primary side to the secondary side. So it doesn't help improve voltage, especially when the load is very high. So usually operator just disable the type changing transformer. Okay, and the voltage load shedding, similar to under frequency load shedding, is very effective way because it's going to directly reduce the load. You push the operating point on the PV curve back